Hello, this is Mrs. James. This is our end of course review, Waves Part 2. If you haven't seen Waves Part 1 yet, you should go back and watch that. Alright, we've been talking about what happens when waves hit things, and right now we're going to talk about what happens when waves hit each other. We could talk about this for light or for sound or for any other kinds of waves, but people often focus on light when they talk about this for reasons that you'll see soon. Alright. Let's say that we have a wave and it's traveling this way, you can see the arrow, and another wave traveling this way, and when they hit each other, they're what we say they're in phase. So the top part of the hill of one of the waves, and that's called a crest, and that's actually a pretty good word to know. Let's write that down. Crest hits the crest of another wave. What happens to those, the combined wave? Temporarily it gets bigger. So it takes the energy of this wave and the energy of that wave and it combines them. Right? Now the same thing happens at the bottom of the wave, and that's called a trough. So when the two waves hit, if they're at the bottom, then those will combine and you'll get an extra, momentarily you'll get an extra big wave at the bottom. We call that constructive interference. So let's write that down too. When they work together to temporarily make a combined larger wave, we call that constructive interference. Alright, well, sometimes when they hit each other though, this wave is going this way, this is going that way. Do you see how we have a trough lined up with a crest? When that happens, they're going to cancel each other out. And you can see here in the picture how troughs and crests are meeting each other. Instead of called constructive, that is called destructive interference. Well, let's actually see what this looks like in something that has moving parts to it. So let's pull up an animation. So here we go. You can see two waves traveling towards each other. They hit. They temporarily get bigger. An example of constructive interference. Alright? Constructive interference. If this was a light, it would be brighter as we have that combined energy. If this was sound, it would be temporarily louder as we have that combined energy. Now let's look down here at this picture. At this picture we're seeing constructive and destructive interference as the waves are hitting each other. Now here it's showing them not hitting, it's showing them separate. You have to pretend they're actually colliding with each other. So when a crest hits a crest, you get a momentary large part. When a trough hits a trough, like right here, you get momentarily a very large downwards wave. We refer to the height of this wave as its amplitude. Alright? Now, notice that our wavelength and our frequency of these waves stay the same. Wavelength and frequency are not changing. So if this was light, the color wouldn't change. If this was sound, the pitch wouldn't change. What's changing again is the height, which is our amplitude. So our sound would be getting louder right here. Our color would be getting brighter. And now you can see though when they hit and they're out of phase, so right now, right now, right now, you see how it got flat there? That means that those waves are canceling each other out right then, which means that it's a less bright or no brightness and a quieter sound or no sound at all. So that again is what happened when waves hit each other. You can get constructive or destructive interference. Alright, now that's kind of a complicated topic. It's really a career. Designing, for instance, a hall where people will go to hear concerts, which is going to be helped designed in part by a sound engineer. And the sound engineer has to think about all those sound waves that are bouncing all over the room during the concert, how they're going to work with each other to either make places where the sounds are louder or places where the sounds are quieter. So this is a pretty important topic for some careers. Alright, now we're going to go to a slightly harder topic called diffraction. And to talk about diffraction, we're going to go look at one of our gizmos. So I'm going to open up a gizmo. Let's make this a little bit, I was trying to make it bigger, but it didn't work. Alright, we'll have to look at it this size. Alright, I have here something called a ripple tank. In a ripple tank, you're pretending is full of water, and we're looking down on a wave. Now, every wave we've seen so far has been from the side view, so you could see the crest and the trough, but this is from the top. So think of the dark lines as crests, the top of those hills of those waves, and think of the white areas as troughs, so the lowest point of those waves. Alright, so there we go, we have these waves going across the tank. Now let's reset it. If I have a barrier and I have a gap in that barrier, I want you to watch what happens to the wave when it hits the barrier. Alright, here comes the wave, crest and trough, they hit the barrier. Alright, now as they go through, look how instead of a straight line, what we instead are forming are circles, kind of as if you had dropped a pebble into the middle of a lake or a stream and it was creating these ripples going outwards. That's what happens when the wave goes through that slit. That's just a factor of wave behavior. And this is part of what we call diffraction. Diffraction has to do with wave behavior when it hits a barrier and an opening. Let's switch briefly to a single central source. So this is, again, if you drop a pebble into a lake. You see those outward ripples? Alright, that's what happened to our straight wave when it hit that gap. Here we have a slightly bigger gap, so you can see that it looks just a little bit different. Alright, now we have to combine this idea with what we just learned about constructive and destructive interference. I'm going to have a barrier with two gaps. So the waves coming through this gap are going to form those circular wave patterns, and the waves coming through this gap are going to form circular wave patterns too. The waves from this slit and the waves from this slit are going to hit each other. So let's watch and see what happens. Here it comes, the straight wave hits the gap, and we start to get there they are, we start to get two different circular wave patterns. Now these are colliding with each other. What I want you to see is how they collide with each other. We get this pattern of dark and light spots. So we get patterns of constructive and destructive interference all over the waves that combine as they come out of those two slits. If I make my gaps at a different width apart, I'm still going to get those patterns, but they're going to look a little bit different. And again, all this is grouped together under that word diffraction, how waves behave when they hit barriers and openings in the barriers. And when scientists first started studying this, and they saw these patterns of dark and light, that's how they came to learn that light would travel in waves, just like water could travel in waves. Alright, if you're interested in more of that, you can look that up again. That would be grouped under the term diffraction. So let's put a little summary here. Wave behavior when the wave hits a barrier or a barrier with a gap in it.